Okay, today we're going to talk about complex ions and coordination chemistry. So, for coordination chemistry, there's a couple of things that we need to be familiar with. And first of all, is that what a coordination compound is. And a coordination compound is going to consist of a complex ion, which is a charged species consisting of a metal ion. Excuse me, surrounded by ligands. Remember, a metal ion is always going to have an overall positive charge because metals are going to give away their electrons to become positively charged cations. They also may have just what's called a counter ion, which is just a typical anion or cation needed to produce a neutral compound, and that could be monatomic or polyatomic. They typically involve transition metal ions, particularly when it comes to the complex ion, because those are the ones that have the most common, not most common, but the positive charges. Now, for ligands are a neutral molecule or ion with a lone pair of electrons that may be used to form a bond to a metal ion. So that lone pair of electrons is obviously going to be negative, and it's going to be attracted to the positive metal ion. So it's not necessarily a bond as much as a kind of a dipole interaction between those two particles. Now, the formation can be described as a Lewis base in Lewis acid reaction. Lewis bases are electron pair donors. I think that's spelled wrong. And Lewis acids are electron pair acceptors. So the ligand is going to be the electron pair donor. The Lewis acid is going to be the electron pair acceptor. All right, so the bond formed, again, it says it's a coordinate covalent bond. Even though they're not really sharing electrons, though, it really is a positive-negative interaction, and that's really kind of the way that we need to think of it. But it can be a pretty strong bond, and that's why they call it a coordinate covalent bond. Now, some common ligands include water, which we refer to as aquo, ammonia, or amine. And remember, water is going to have some lone pairs, off of the oxygen. The amine group will have the lone pairs off of the ammonia. Off the nitrogen. The chlorine obviously will have lone pairs surrounding it as well. So as you're thinking about this, cyanide or cyano will have lone pairs off of the end of the nitrogen. Hydroxo will have lone pairs off of the oxygen. And then bromo, very similar to chlorine because it's got a similar Lewis structure, will be off of the edge of that. Same thing, with the oxo, or the O with the 2- charge. And then carbonato will be off of the oxygen as well. So all of these contain atoms that have lone pairs. Nitrogen will have the lone pair for the nitro. And then oxalato will also have the lone pairs off of the oxygen. It was just kind of squeezing them in there where I could. But all of these contain atoms that have lone pairs that, again, will attract themselves to those positive metal ions. Okay, the number of ligands that will attach to the central metal ion is what's called the coordination number. 2, 4, and 6 are the most common coordination numbers, and oftentimes the number of ligands is 2 times the metal's oxidation number. So for example, a lot of times with aluminum, if aluminum has a 3+ charge, I know that's kind of tough to see, it will end up with 6 ligands around it, okay, and that's just the way that it sets itself up, and just some common patterns that you will notice. Okay, now we're going to talk about some naming. And again, I'm going to run through these. You're going to do some practice, and hopefully that will help make sense of it all. But the complex ions are named by giving the number and the name of the groups attached to the central metallic atom, followed by the name of the central atom with its oxidation number indicated by a Roman number in parentheses. Okay, what? So for example, this one right here would be hexa aquo chromium 3. Hexa is going to come from the 6. So there's the number of the ligands, or the number of groups, the name of the group, which is aquo, okay, because you've got the H2O, and then it's attached to a chromium ion, so we put chromium, and then the 3 just simply comes from the charge. All right, so that's where that is going to come from. Now, the anions are going to be opposite. The good news is some of it's still the same. You still need the number and the name of the group. You're going to put the name of the central atom, but this time we're going to change it to 8. Oops. The ending to 8, okay? So, excuse me, this one right here would have hexa, which refers to the 6, chloro, which is the ligand that's attached, and then we take platinum and we change it to platinate. I always remember you change the anions to 8. It's just what sticks in my head. And then the 4 is the charge of the metal ion. Now you may be going, okay, well it's got a 2 minus on it, so where did that come from? Well, you can always work backwards. We know that the overall charge of the ion is 2 minus. We know each chlorine has a 1 minus charge. So you've got 6 minuses from the chlorines. So if you know the end result is 2 minus, 6 minus is the charge of the chlorines, then you know that the platinum has to be 4 plus. Okay, now I know this one does not follow the, 2 times the oxidation number is how many are there. That's just a general rule. The good news is most of the time you're either given the name and you have to do the formula, or you're given the formula and you have to do the name, so you can always work backwards from those. Okay, you guys are going to do some work in shock, so just some rules on this stuff. Again, the ligands are always named before the metal ion. Ligands always have special endings. Refer to the handout in shock that you're going to see for what these, what the ones are that you're responsible for. O is used in place of "ide" for anions in some of these rulings. And for anions that end in "ate," the O is also used in place of the E. Okay? So for neutral ligands, the name of the molecule is used with the exception of, remember, we saw water was aquo, we had amine, and then some of these other ones are going to have other names as well. So just some differences there. Ligands are always named in alphabetical order, so that's how we write them properly. And we use the prefixes di, tri, tetra, penta, and hexa to denote the number of simple ligands. Mono is omitted for 1. We don't have to include that. Maybe. Okay, more complicated ligands use some of the other prefixes like bis for twice, tris for thrice, tetrachus for 4, pentachus for 5, and hexachus for 6. And we'll see some of those examples so that we can differentiate between these. Now, the prefixes do not affect the alphabetical order. Okay, so the ligand names themselves are in alphabetical order, but the prefixes do not change the alphabetical order for those. Okay, oxidation state of the essential metal is always designated by Roman numeral in parentheses following the name of the complex ion or molecule. Numeral can be omitted if the metallic cation does not exhibit variable oxidation number. So for example, we know silver is always a 1 plus. So you don't have to put the 1 there for silver. Some people do if it's a complex ion, but for the most part you can leave that off. For anionic complex ions, those with negative charges, we've already seen this, but the overall suffix of "ate" is added to the name of the metal. Okay. And the English name is used except for the following exceptions. You've got copper, gold, iron, lead, and silver, and tin, and we'll see some of those in the handouts as well. We go back to their Latin names. Cis and trans may also be used, and you'll see this in shock as well. And we'll do some more work on this a little bit later. Okay, so let's just do some samples, because that's kind of where I think we need to be right now. For this example right here, a couple things to point out. We've got 2 ligand groups, okay, right here, and it's attached to our chromium metal, and it has an overall positive charge. So this one is going to be tetra-aquo dichloro chromium 3. Remember, the 3 is going to refer to that chromium, that's a bad 3, has an overall 3 charge. I work backwards because I know the overall positive charge is a +1. I've got 2 negatively charged chlorines, so I know that chromium has to be a 3 there. Okay, the next one we have is pretty similar. All right, we're still dealing with the chromium and the same ligands, but this time we've got diaquo for the 2, we've got tetrachloro for the 4, chromate, okay, in 3. Now the only reason we changed the 8 ending here is because it was a negatively charged. Anytime it's an anion, we change it to a negative ending. All right, next one we've got is going to have trans in it, and En is also an abbreviation for a larger ligand that we'll see. If they put the trans in front of it, just add it in front of the name. Okay, so for right now, and we'll get into what trans and cis mean a little bit later, but you've got trans chloro. Okay, that's for the Cl. Bis and ethylenediamine, which is this one. You'll see where that one came from. Remember, some of the more complicated ligands, we'll use bis and tris and those. Then you've got hydroxo. Okay, that's going to come from the OH. And then cobalt 3. We didn't change it to ATE, or the 8 at the ending, because it is positively charged. And again, you work backwards to figure out the charges. You've got an OH that has a 1 minus. You've got a chlorine that has a 1 minus. The overall charge is a 1 plus, so you know that cobalt had to be a 3 plus. All right, let's see, this may be the last one here. Okay, next one we've got, this is a benzene group. Remember, benzene is that 6-carbon ring, so you've got benzene, tetra, carbonyl, manganese, 1. Okay, the 1 is going to refer to manganese's charge, where we get that from. Excuse me, on those as well. Okay? All right, now let's do the opposite. So let's say we were given the compounds and we have to name them. All right, we have potassium, hexacyanoferrate 3. Potassium, plain old potassium. Okay, this is, remember, this is a compound. This isn't just the complex ion. So potassium is really its own, you know, this is the counter ion we were talking about. You've got hexa for 6, cyanoferrate, and then 3 would be the overall charge on the iron ion. Now, it's got that 3 here because the charge on the complex ion would have been a 3 minus, so that's why you need the potassium, because it needs 3 pluses. Okay, the next one for the name, this would be bis. It's going to be 2 of those right there. You've got ethylenediamine, which is the E in there, dinitro, iron 3, sulfate. Okay, again, you'll notice that the complex ion, if you need more than 1, is going to be in brackets. Now, the complex ion had an overall charge of a 1 minus, so that's why there's 2 of them paired up with the sulfate, just like we do with regular ionic compounds. And then for this one here, you've got sodium, you've got tetrahydroxo, and then aluminate. Okay? Now, the reason that this ends up with the ATE ending is that the overall charge of this complex ion is going to be 1 minus. Where's that going to come from? Each hydroxide has a 1 minus charge, so you're going to have 4 minuses here with the hydroxide. You've got a 3 plus for your aluminum. I know it's tough to see, so you get an overall 1 minus charge. Okay, I'm going to stop there. I hope that was helpful. Ask lots of questions. We will do lots of practice.